Hey everyone, welcome to This Explainer. Today, we're embarking on a seriously fascinating journey right into the architectural foundations of the digital world. Think of this upcoming content as your master builder's toolkit. We're going to break down exactly how the software and systems you use every single day are engineered straight from the ground up.
But before we get into the heavy lifting, we've got to pose this fundamental question. How do machines actually understand and organize data? It's pretty easy to take for granted, but this is the core problem addressed right at the start in Module 0 of our source material. Without organization, data is honestly just chaotic noise.
Well, the answer to that question lies right here in our syllabus definition. A data structure is all about organizing information for machines and humans to understand, which helps solve real-world problems quickly and logically. This is the master builder's fundamental rule. It's the absolutely crucial step you have to take before a single line of actual code is ever written.
Okay, let's dive into the specifics here. This is a comprehensive 3-credit course, officially coded as CSPC 303. Now, to even get in the door, it requires a prerequisite in C programming. What's fantastic about this is that it directly addresses core engineering outcomes, things like complex problem analysis and the meticulous design of practical solutions.
Here's our roadmap for today. We'll start with foundations in algorithms and complexity, then move on to building blocks with linear structures, and branch out into nonlinear structures. After that, we'll look at optimization with sorting and hashing, jump into real-world system applications, and finally wrap it all up with course assessment and outcomes.
Section 1. Foundations, Algorithms and Complexity.
So before we can really build anything, we have to understand the math and physics of our workspace, right? Module 1 introduces us to the precise tools we need to measure that physics. It covers the RAM model of computation and crucial analysis metrics like time complexity and space complexity. We use asymptotic notations like big O, omega, and theta to mathematically evaluate exactly how efficiently our algorithms will perform. I mean, we have to know if our code is going to run in 1 second or 1 year.
Mastering these analytical tools right out of the gate is absolutely vital. It prepares students to intelligently identify the most appropriate data structures for very specific computational constraints as they move forward into the heavy coursework.
Moving on to Section 2, Building Blocks, Linear Structures.
These are the fundamental raw materials for our digital construction. We've got stacks, queues, linked lists, and arrays. To make this a bit more tangible, think of a stack like, well, a literal stack of heavy plates in a cafeteria. The last plate you put on top is the very first one you take off. A queue is exactly like a line for a printer. It's first come, first served. These concepts make abstract computer memory incredibly logical and manageable.
Section 3. Branching out, Nonlinear Structures.
Now, there's a really sharp contrast as we move forward here, because real-world problems often require more complex blueprints than just a simple straight line. While linear data structures involve sequential processing, like that single printer queue we just mentioned, nonlinear data structures involve hierarchical and interconnected branching. We are basically graduating from simple lines into the incredibly rich, multidimensional territory of trees and graphs.
Module 3 covers binary search trees, AVL trees, and deep graph traversals. And the crucial point here is how this maps directly to our everyday reality. When you open Google Maps and it instantly finds the shortest path around a massive traffic jam, or when a telecom network successfully routes your data across the globe, it is utilizing these exact graph matrix representations under the hood. Pretty wild, right?
Section 4, Optimization, Sorting and Hashing.
This stage is all about learning to optimize and organize our digital filing cabinets for lightning-fast retrieval. This builds into the precise mechanics of hashing, which is a brilliant 3-step process. First, you create the symbol table. Second, you apply hashing functions. And third, you use collision resolution techniques like chaining or linear probing. This vastly simplifies finding data, purely because you don't have to painfully search through the entire database row by row.
Alongside hashing, we get into powerful sorting and searching tools. We're looking at insertion, quick, merge, selection, and heap sorts, plus the stark difference between linear and binary searching. The course emphasizes that evaluating your data and proactively choosing the absolute best sorting algorithm is a core engineering outcome here.
Section 5. Real-World System Applications.
This is where all those previous theoretical tools combine to actually build modern technology. Just look at the massive, exciting scale at which these operate. Relational databases completely rely on B+ trees and hash indexing. Software compilers use syntax trees and symbol tables. Global networks use routing tables. Even cutting-edge machine learning heavily relies on decision trees and KD trees. Data structures are quite literally the structural DNA of the modern tech world.
Now, what's really interesting about this slide is that the explicit learning objective for Module 6 focuses heavily on gaining insight into how abstract data types are directly mapped to real-world data models and system-level functionalities. It proves that this isn't just dry theory, it's entirely about solving complex, high-stakes computational challenges.
Finally, Section 6, Course Assessment and Outcomes. You can think of this as the final boss battle of the course. Breaking down the 100 total marks, we can see exactly how the grading is distributed across the semester. Continuous assessment accounts for 20 marks, the mid-semester exam takes up 30, and the end-semester exam carries the heaviest burden at 50 marks.
But it's totally critical to note how that end semester exam is weighted. It heavily tests the later, more complex material. Only about 20 to 30% covers the early pre-midterm content. A massive 70 to 80% is heavily weighted on those advanced post-midterm nonlinear structures and optimizations we talked about.
And the continuous assessment is really designed to keep students actively practicing. It's not just a quick multiple-choice quiz. It specifically requires a minimum of 20 numerical assignments alongside flipped classroom activities to ensure deep, active engagement.
I really want to highlight this fantastic quote from the program outcomes listed in the syllabus. It asks students to recognize the need and be able to clearly explain why it is vitally important to keep current regarding new developments in your field. Technology is always relentlessly evolving, but mastering these fundamental data structures gives you the timeless logic required to adapt to anything new that comes your way.
So, I'm going to leave you with this final provocative thought. Are you ready to master the blueprints of the digital world? Data structures are far more than just code. They're the elegant architectural logic that powers our future. I really hope this explainer has sparked your curiosity to explore computer science even further. Keep learning and keep building.